Welcome everyone to the last part of the mini course and also the last part incidentally of section 4.2, where I will explain how to use Weyl calculus to rigorously prove semi-classical equations describe accurately what is going on in a crystalline solid that is subjected to external fields. So this was the picture that we initially had in the first part of the talk. And then we derived the so-called band picture for the unperturbed Hamiltonian and this operator has a purely discrete spectrum that accumulates at infinity, etc., etc. And for us, the important thing is that it leads to the so-called band picture. So locally, the energy bands, which is the collection of the eigenvalue depending on K, on crystal momentum K, which is an element of torus in reciprocal space, in momentum space, and away from band crossings, what you would get are locally analytic functions. Also, once you choose the phases appropriately for the eigenfunctions, you would also get locally analytic functions. At least that's always possible, again, away from band crossings. And the simple setting that we had in mind is where the relevant states that are interesting to us are separated by a gap from the others. So this red band, E3, has no intersections with the bands below and with the bands above. So in this sense, it is isolated, and furthermore, to avoid internal degrees of freedom, we will assume that it is non-degenerate. So the dimension of the eigenspace associated to E3 is equal to 1. So the presence of these external fields, the external electric and the external magnetic field, can be taken into account in a single electron picture. So this is the so-called single electron approximation. Where the potential is generated by the nuclei and all other electrons. So you're neglecting electron-electron interactions. So to account for all of this physics, we have proposed the following Hamiltonian. We have minus Laplace minus a of x epsilon x hat, where epsilon was the semi-classical parameter that compares the microscopic scale on which the periodic potential varies and the macroscopic scale on which the external electromagnetic field varies. Then you have a periodic potential, and then you have an external potential that generates the electric field. So just to color everything consistently, so the magnetic vector potential A is associated to the magnetic field, which is blue in the picture, and the scalar potential generates the electric field E. So the electric field E is just minus the gradient of phi. So what we would like to do is we would like to have a semi-classical limit for this type of system once we choose a particular band. So this is important. So we for example, we can pick the band E3. And to just abbreviate the assumptions, let me call it an isolated non-degenerate band. And I call it E star. So star stands for a specific band index, in this case E3, with the Bloch function phi star, also depending on k. So now let me give a vague version of the semi-classical limit and then make everything precise and include a sketch explaining to you how to prove it. So the semi-classical limit, so this here is the semi-classical limit. So under the technical assumptions given below, so to any isolated non-degenerate band of the unperturbed operator, let me call it E star as before. The semi-classical evolution generated by, and now let me give you first the Hamiltonian and then the equations. So let me call it the semi-classical Hamiltonian. So this is E star of k plus phi of r minus epsilon now we have to sum over all of the indices. So we have to sum over Bjn, so the components of the magnetic field, times the components of the so-called Ramal-Wilkinson term. And the equations of motion. this is important because we're not just dealing with canonical Hamiltonian equations or even those with a magnetic field. So we have a magnetic term, then we have the canonical entries, and then we have an additional term, which is the so-called Berry curvature. And this is equal to the R gradient of H semiclassical and the K gradient of H semiclassical. These approximate the full quantum evolution. In the following sense. Well, first of all, we have to pick our relevant states. So let me put that in purple. So let me just be a bit vague and say for states associated with E star. For bounded times, as usual, and semi-classical observables, F. So the point, and that's why I'm going to color semi-classical observables as well. So this semi-classical observable is not some vague notion, but in the literature that I'm relying on here, this has a precise mathematical definition. So later on I will give you a reference to a precise mathematical definition. So this is not vague, it's just that I'm omitting the relevant function space. And then you do have what you would expect to have, namely if you compute the operator norm of, well, for reasons that will become clear a little bit later on, let me use the Fourier transformed Hamiltonian essentially. But of course the discrete Fourier transform, or the variant that I'm using here, the Zach transform, is unitary, so this doesn't change anything. So what I'm writing out here is what we call the quantum mechanically evolved observable. I just wanted to make it a little bit more explicit. And I'm comparing this with the quantization, the magnetic quantization of the semi-classically evolved observable F. And then I have to add a projection pi. And the reason I have to, I colored this projection purple is that, well, this is what I mean precisely for states associated with E star. What I mean is states that are taken from the range of this projection. So for these states that are, morally speaking, supported by this band, be it just a wave packet or really something delocalized, for any of those, can I replace the quantum evolution by the classical evolution in the sense of an Egorov theorem? And of course, this a priori, the simple proof holds for observables that are semi-classical, and that implies that they are quote-unquote quite nice. So for example, they quantize to bounded operators. Of course, if you look at the proof, at the structure, you could probably push further, but then you would just incur additional technical debt that you would have to solve. So let me also color the semi-classical evolution. So that is generated by, of course, the semi-classical equation. So this is the theorem that we would like to prove in the end. And before I'm going too far into the proof, let me just make a few comments about the literature. So the first version of this was proven by Panati, Spohn, and Teufel. In 2003. But there have been improvements to this initial paper. So there's already an improved exposition in Stefan Teufel's book that came out roughly at the same time. And just to give you an idea, what was the, let's say, the one thing why there were follow-up works, the one of the assumptions that they had to make, so this was before magnetic Weyl calculus was fully developed, so they had to assume that not the magnetic field has components CB infinity, but the vector potential has to be smooth bounded and have bounded derivatives. And why is this significant? Well, it is significant because this excludes the very important case of a constant magnetic field. This was remedied by Denitis and myself in 2011 was the publication. So this was an extension to constant magnetic fields, essentially. Of course, it's not just constant magnetic fields. So here the magnetic field has to be smooth bounded and have bounded derivatives. And this includes, in particular, the case where B is constant. And then I think another worthwhile addition was the work by Stiepan and Teufel in 2013. And here the important contribution was that they could extend it to strong constant magnetic fields, where the so-called Bloch bundle is non-trivial. What this precisely means is beside the point for the purpose of this talk, for this mini course, but I think it is a significant technical improvement. And they also proposed a different derivation. I will follow more or less the derivation of the first two works, because it's a little bit clearer to see what happens. And lastly, I think for several reasons, I would like also to mention a work of Denitis and myself about ray optics. And I think this is interesting for two reasons. First of all, we apply the method proposed by Stepan and Teufel to Maxwell's equations, essentially. And I think I would like to mention it, not because I want to push my own work. That's not the point. I would like to say that these methods also apply to classical waves. So if you have a classical wave, then under certain circumstances you have a ray optics limit or geometric optics limit, and you can use semi-classical techniques to prove them rigorously. And this is what we do. All right, so this just gives you an overview. Let me summarize the assumptions. I think I've mentioned all of them earlier, but I think it is worthwhile to just collect them in one place. So let me start with the periodic potential. So I'm assuming that the periodic potential is in L infinity, and as the name suggests, periodic with respect to some lattice which I call gamma. And of course, gamma is assumed to have the full dimensionality of the space. I'm not claiming that any or all of these assumptions are optimal, but these are assumptions where I know that the theorem holds true. Then we place assumptions on the magnetic field and the electrostatic potential phi, namely they are of class C infinity B. And the associated vector potential shall be in a polynomially bounded and smooth. So this is the assumption on the external fields. And then the last one, that's the so-called gap condition. And here we assume that the relevant band E star is non-degenerate and isolated. All right, so these are the mathematical assumptions. I could, of course, state this using distances and the spectrum, but I think in this case there's no chance of confusion, and it's clear how to translate this into mathematics, into equations rather. And now let me give you a sketch of the derivation. And the derivation, you will see, already contains more steps than you might actually initially assume. So the first step is to rewrite the Hamiltonian, or rather the Zach transform, which is essentially the discrete Fourier transform. As the magnetic quantization of an operator. So this gives us, this first step gives us access to magnetic Weyl calculus as a tool. Then in a second step, we have to identify the relevant states. So just to make this precise, this essentially means we're going to explain what this projection pi epsilon is, and in what sense we can say that it is associated with the band E star. Okay, then we have to add an intermediate step where we approximate the full-time evolution by the time evolution given in terms of an effective operator. And this is an important ingredient in the proof of the semi-classical limit. So this here gives us the symbol, so the function, the operator valued function on phase, well, in this case, scalar valued function on phase space H effective. Then we do an initial semi-classical limit for H effective. And then in the last step, we have to eliminate the apparent dependence on the choice of Bloch gauge. And only once we do this, so here we have to use we have to use effective variables. for the semi-classical equations. So this would be quite a lot, and if I went into all the detail, all the gory details, this would be quite ununderstandable. So let me focus on a few key aspects. So the first one that I would like to highlight is how to rewrite the Hamiltonian as the magnetic pseudo-differential operator, the magnetic Weyl quantization of an operator-valued function. So this here is step one. So here we would like to rewrite the original Hamiltonian as the pseudo-differential operator associated to the function h. So let me just first of all write down the left-hand side. So here f h epsilon of a f gamma inverse. If you do the computation, then you get minus I gradient plus k hat. So that's multiplication operator in k, minus a of I epsilon gradient in k squared plus v periodic y hat plus phi I epsilon, epsilon is missing, gradient k. So as I said before, this is the so-called Zach transform, which is a version of the discrete Fourier transform. And if I propose the function, and now this is an operator-valued function, so it's a function in k and in r. Sorry, I made a mistake. So I have to delete the vector potential. That's absolutely important. So this here you will recognize as the sum of the periodic Hamiltonian in k plus phi of r. And this is an operator on, for r, fixed r and k, on L2 over the d-dimensional torus, this time the torus in real space. So this is defined on the same space as this here. And I'm claiming that this is indeed the function for which you have the claimed equality between the Zach transformed perturbed Hamiltonian and this here. Of course, what I'm doing here is not quite innocent, but it's consists all of solvable problems that indeed have been solved. So here I'm using an extension of Weyl calculus to operator-valued functions. what is even more complicated, unbounded operator-valued functions. So this, if I were to attempt this, this would be kind of boring and very, very technical. So let me just give you the upshot, which is everything works as before, mutatis mutandis, so after changing what needs to be changed. But everything we have learned about Weyl quantization and, for example, the product is really the same as before. For example, you still have a notion of operator-valued Hermander symbols, and for those you have good composition properties. Of course, let me add quotation marks because it's here a little bit more complicated as you're dealing with unbounded operators or unbounded operator-valued functions. But you still have a composition law of Hermander in terms of Hermander symbols, and you have, importantly, an asymptotic expansion. So f val g makes sense, and it's still f times g pointwise product of operators now minus epsilon I divided by 2. The magnetic Poisson bracket of f and g plus order epsilon squared. So the point is, it works the same as before. You just have to define very carefully what these objects mean. Let me be just a little bit more precise. So here, the building block operators well, first I have a position operator, which is I epsilon gradient k. Here in the definition of the domain, you have to include some twisted boundary conditions. But this is not really interesting for, or let's say, I don't want to get too much into this for the purpose of this talk here. And then you have kinetic momentum, which is multiplication with k minus a of capital R. And so we have accomplished the first point. What this gives us is, for example, access to rigorous expansions of the operator product using, of course, the magnetic Weyl product. And this allows us to do rigorous perturbation theory. And this is also useful if you're looking away from semiclassics. So if you want to derive effective dynamics, for example, that in the form of tight binding operators, you can still use magnetic Weyl calculus. That's a very good tool for the job. Wrong page. Oops. Okay, here we go. So the second point that I would like to spend a little bit of time on is the identification of relevant states. And I think there are two natural conditions that come out of a careful reading of the wording. So we would like to identify states that are associated with a relevant band. And in this case, this is the band E star. And these states must have, of course, a good semiclassical limit. So let me first take a guess with one. So if we think about it, then and if we pretend for a moment that this projection that I introduced in the statement of the theorem has an expansion in epsilon, then it seems natural to require that the leading term is the projection onto the eigenspace of the relevant band. So here pi 0 of k is just the rank 1 projection associated to the relevant band. So this gives you an, let's say this of course a guess, but what you can do is you can actually, starting from this here, you can construct this operator in a systematic fashion. But I think before I show you how to do this, I think the important point is condition B. So let's say what is the type of condition that we have in mind? Well, one thing that must not happen is that under the time evolution, if you start with a relevant state, with a state that is associated to this band, then it must not leave it if you evolve it in time. So the central condition here looks something as follows. If you apply the, let's say, the full quantum evolution, to the relevant subspace. And this is just the range of the projection that we introduced earlier. Then this should be preserved under the dynamics, at least modulo an error that is negligible. And here the technical, so let's say the translation into rigorous math is order epsilon infinity. But this is good enough for our purposes. And what does this mean? Well, it means, so if one equivalent way of writing this is to require that the Hamiltonian in the correct representation commutes with this relevant projection. Actually, what we have to do is, as before, we have to replace the exactly commutes by order epsilon infinity in operator norm. And of course, we have to require, if we think about constructing such a projection, is that one of the things that we need to impose when we construct pi a epsilon order by order is that it is indeed an orthogonal projection. Again, modulo order epsilon infinity. So the very nice thing about this is that once we have made the connection to pseudo-differential theory, and if we for the moment assume, so this is an assumption, but this assumption is justified by an explicit construction, that this projection is a pseudo-differential operator at least modulo order epsilon infinity. Then what we can do is we can just translate this commutator into a Weyl commutator, because if you remember, this here is just op A of H. So this simplifies to the Weyl commutator of H and pi, where small pi is the symbol of capital pi a epsilon. And here, the small pi should be a Weyl projector. So if we replace the operator product with the Weyl product, it should satisfy the defining relations for a projection. And indeed, this is how you can actually construct this operator. But a more straightforward way is suggested by functional calculus. And what you do is you construct the symbol. So first of all, with this solution, you actually prove that what you get is a suitable symbol from a particular symbol class. So you're writing the projection. Since it's a projection, it's reasonable to think of it as a contour integral. And indeed, this is exactly the right approach. But you're taking the resolvent with respect to the Weyl product, to the Weyl product. So this is the so-called Weyl resolvent. And this Weyl resolvent satisfies the relation that you think it should. So if you take the Weyl product of H minus Z with the Weyl resolvent, well, you get 1, at least modulo order epsilon infinity. And C of R and K, that's a contour. And this contour only encloses E star of K plus phi of R. And in fact, what you can do is, maybe let me make this modification. You can choose the contour to be locally constant. And that is because, everything changes smoothly, hence continuously with K and with R. That's because isolated band functions are analytic, hence smooth, hence continuous. This here was smooth and bounded by assumption with bounded derivatives. So we can choose this to be locally constant in a neighborhood of R0 and K0. And hence all the properties of pi are directly inherited from the so-called Weyl resolvent. And this can be constructed order by order, perturbatively, and not surprisingly, the 0th order is just a projection onto the onto the nth band, onto the relevant band of the unperturbed operator, and then of course we have further corrections. And let me just say that in principle, of course, you can expand pi order by order. So you can write pi as an asymptotic series. And the pi n can be computed recursively. And everything in principle is completely explicit. But for the semi-classic limit, there's a nice fact. It turns out, and this is not quite trivial, but if you look at the formulas in the right way, you get cancellations. In fact, only pi naught is needed. So this is not at all obvious. So you would expect, since semi-classical limit are up to order epsilon squared, that you would probably also need pi 1, but you don't need the explicit form of pi 1. You just need to know that this pi and hence the capital pi a epsilon exists, and that's something that you can do. So the next bit is the identification of the effective Hamiltonian, and I would like to be brief here. And what do we do here? So morally speaking, and that's because I'm skipping some steps that are important. What you have is we can directly express it in terms of symbols, because by construction, pi is a Weyl projection and commutes up to order epsilon infinity with h. Then if you look at the original form of the semi-classical limit, then you see we have this projection here, and we have the operator op a h here. And because these operators commute, I can actually push a second projection to the other side, and I can also replace this operator here by pi a epsilon times this operator times pi a epsilon, and translate it to the level of symbols. I just get this here. And because of everything that I've said before, this operator has an asymptotic expansion. So we make this clear here. So it has an asymptotic expansion. We will only need the first two terms, so the leading order term, the so-called principal symbol, and the first subleading correction. And if you do a little bit of computation, what you get is the following. Well, not surprisingly, you just replace, to leading order, you replace the periodic operator with E star, with the band function. Then you have to add the electrostatic potential. Okay, that's also relatively clear. And then we have a cornucopia of subleading terms. Let me be a bit careful in explaining what they are. So first we have what is essentially the Lorentz force. So you will see that the first term is the jth component of the electric field. And now we also get the magnetic field term. And this is multiplied by the so-called Berry connection. I've mentioned this already when I talked about the works of Sundaram and New. And then I have the so-called Ramal-Wilkinson term. For the sake of completeness, let me write down what these terms are. So this here is the Berry connection. And this is just I times the scalar product of phi star evaluated at k, and with the gradient of phi star of k. And this is the scalar product on the L2 space over the real space torus. And importantly, so this term, and let me make this red, this term here is Bloch gauge dependent. So if I change the notion, if I change my gauge, so if I multiply my Bloch function by a phase, and the phase, let's say, is analytic or it's smooth at least, then I get an additional term to the Berry curvature, which is the gradient of this phase. So this term is gauge dependent. And the term M, that's the so-called Ramal-Wilkinson term. So let me just write it out. So this is the real part of I have, and then you take the scalar product of the kjth derivative of phi star, and you take the scalar product with h periodic of k minus e star of k applied to the knth derivative of phi star. And physicists like to think of this term as a sort of effective magnetization of the relevant band. So the point is just that you have an explicit equation, and what you do is you use a Duhamel argument. So the fundamental theorem of calculus. To show that if you look at states, at relevant states, you can replace the full time evolution remember op A of h. This was up to a variant of the discrete Fourier transform, just our original Hamiltonian. So there's no approximation on the left. And I subtract from that the effective time evolution. And I'm just looking at states from the relevant subspace. Then this is equal to order epsilon infinity in operator norm. Of course, if I truncate this asymptotic expansion, let's say after first order, this arrow will grow to order epsilon squared, right? Because the accuracy of my Hamiltonian in this case is only order epsilon squared. So if I just use the first two terms, then this is the best I can do. In this derivation, I was skipping over a lot of details. So the derivation that I'm following for the most part actually involves a change of representation facilitated by unitary, and this unitary is also a pseudo-differential operator, also the Weyl quantization. Although you could also use an entirely different approach, first given by Stiepan and Teufel, which uses very different, more condensed arguments where it's a little bit harder to see what is going on. But nevertheless, you arrive at the same correct result. I will also keep step 4 relatively brief because, let's say, unless you really insist on me giving the details, and because this is a video, I will not be able to oblige. We will do a semi-classical limit in terms of using an Egorov theorem. And we're doing this for H effective. Of course, one of the things that we need to clarify here is the notion of semi-classical observable. And the important thing is that these are scalar valued Hermander symbols. So why scalar valued important? Well, in general, so if you think of small h, this was an operator valued Hermander symbol. And not surprisingly, you can also look at those that are proportional to the identity, and those are scalar Hermander symbols. If you're really interested in a precise definition, I refer you to definition 5.1 in my work with Giuseppe De Nittis from 2011. So point is, there exists really a rigorous mathematical definition. So this is not just vague, a vague notion like quote unquote a nice function or so. So now we can use an Egorov type theorem to prove a semi-classical limit. And let me just write it in words, because even I've given the assumptions and you can read up on the details. But for any semi-classical observable, F, the full quantum dynamics can be approximated by semi-classical equations of motion in the usual sense of an Egorov theorem. So what do these semi-classical equations look like? Well, they are just the magnetic equations. So R dot is plus K derivative of H effective, and K dot is minus the R derivative of H effective plus the magnetic term B times R dot. These have the flow phi effective because they're generated by H effective. For bounded times, so again, this is because of the Grönwall lemma that is implicit. In the usual sense. And now let me just use the shorthand notation. So we have the quantum mechanically evolved observable. Then we subtract the classically evolved observable. And of course, this is only for states from the relevant subspace. And the arrow we make here is order epsilon squared plus something that is linear in t as long as small t remains bounded. So I don't really want to dwell too much on this, except pointing out one important problem. And that is that H effective, and therefore the flow phi effective depend on the choice of Bloch gauge. And that means that these equations of motion do not have a good physical interpretation. They're not useless. You will see you can arrive at the correct equations, but not without a little bit of extra work. So these, the problem is that the variables are not physically meaningful in the same sense that if you have if you are considering a classical system with magnetic field, then it is only the kinetic momentum and not bare momentum that has a good physical interpretation. And the same is true here. So this is the last step, and we're nearing the end of this mini course. And what we have to do now is we have to change to effective coordinates. So the starting point here is that only wave functions psi from the range of my projection, which is again modulo order epsilon infinity, my relevant subspace, are relevant. And one thing that we confirmed already is that if I take the energy expectation value for relevant states, so then I just have the scalar product of psi with op A of H psi. Because these are from the relevant subspace, I can introduce the projection free of charge. And once I bring the projection onto the other side, you already see that this is nothing but the expectation value of the magnetic Weyl quantization of pi while while h while pi with respect to psi, and this guy in parentheses is nothing but H effective. So this is a way of writing. We could equivalently have computed the expectation value of sorry, I'm missing the quantization here, of the magnetic quantization of H effective. So we can replace H with H effective for the purpose of computing expectation values with respect to states from the relevant subspace. And the same argument holds verbatim for other observables, for other semi-classical observables. And two particularly important semi-classical observables are called, well, position and momentum. And as you can imagine, if you want to compute something like position expectation values and so forth, you actually will have to sandwich everything with projections. So this leads to R effective which is pi while r while pi. And if you compute it, the first two terms is just r, okay, that's the boring guy, plus epsilon times a of k, which is the Berry curvature, the Berry connection, not the curvature. The curvature will come into play in the next step. And you see that here, so this is the same as in the paper by Sundaram and Yu. And here literally the Berry connection plays exactly the same role as the magnetic vector potential. It just appears for the position coordinate rather than the momentum coordinate. And also the effective momentum coordinate gets modified. And what you get is, well, you get the leading order term, which is the boring one, plus epsilon b of r times a of k. So again, the Berry curvature enters. And to understand how this intertwines, the following proposition is quite useful. So let me call the map so I'm defining a map T effective, which maps R and K onto their effective counterparts. And then for semi-classical observables, we can we have a faster way of computing F effective, namely F effective is just the composition of F with this coordinate transformation, at least up to errors of order epsilon squared, and for our semi-classical purposes, this is good enough. And just as a reminder, this also implies the following. On the level of operators, if you sandwich F between projections, what you can do is you can replace this by this coordinate transformed original semi-classical observable, and then you could keep both projections, of course, but it's easier for the proof later on if you just keep one. So this tells us that basically if you want to compute expectation values, instead of having to compute this F effective, you just have to do a coordinate transformation. At least if order epsilon squared is good enough for you, which for us it is. And now let's come to the final conclusion, so to speak. So we need to just combine two things. So the first thing is a proposition that connects the two Hamiltonian equations of motion. So if we rewrite the semi-classical equations that we first derived, in terms of the original coordinates, then if we rewrite this, if we do a consistent change of variables, so if we rewrite these in terms of effective coordinates, this yields, and this is the important point that I want to impress upon you, Bloch gauge independent equations and what do these equations look like? Well, they're the ones that I wrote down in the introduction. So you have to replace R with R effective. And in a lot of places, it looks like you're getting the same terms, but already here, you're getting an additional term, namely you get the Berry curvature, and now you have to, of course, take the time derivative of R effective and K effective. And then on the right hand side, well, you have the gradients with respect to R effective and K effective. If I remember correctly, relating the two gradients with one another was the part that I found the most tedious. And then you have the semi-classical Hamiltonian, and the semi-classical Hamiltonian is, like I said, just H effective in the new coordinates. So let me avoid copying all the terms down again. Here the important point is that you just have to use the correct coordinates. And another fact is that the flows well, the first one is the semi-classical flow, and the other one is, well, I have to transform back and forth. So the flows the semi-classical flow and the transformed effective flow agree up to, again, order epsilon squared, which is good enough. So how do you prove this? It's really just a variable substitution that you have to carefully implement, and that's that. And then once you combine everything, then you get the final result. And that is under the assumptions. Let me capitalize assumptions because I'm pointing to a particular mathematical statement. Stated in step 1. Semi-classical observables have a semi-classical limit for bounded times. So, of course, this is a shorthand notation for what I wrote earlier, but let me copy it down once more in all of its glory. Using the original operator. So here I'm using the time evolution of the quantum time evolution, the full time evolution. And of course, I'm doing everything only for states from the relevant bands. That's why I will add this projection at the end. And if I compare this full quantum evolution with the semi-classically evolved observable for states that are from the relevant subspace that is associated to this non-degenerate isolated band, then this here is indeed order epsilon squared times absolute value of t. So in this precise mathematical sense, you have a semi-classical limit. And you've seen that magnetic Weyl calculus was able to do this, even though it looks quite complicated. Conceptually, it is still quite similar to just a regular semi-classical limit. It's just that you had to take care of a lot more things under the hood. And I hope you were able to take something useful out of this mini course. I've tried to split it up into parts so you can rewatch it. You can watch parts of it as you please. And for the participants of the workshop at the Lawrence Center, I hope you have a very, very nice virtual conference. Hopefully the next time will be in person again. Thank you very much.